The following content is created by Dr. Avitech. Your support and donation will help me continue to offer high-quality educational resources for free. To make a donation, send an email to 6drcyril@gmail.com or comment donations below.
Welcome back, guys. In this video, we're going to be finding the Laplace transform of sine and cosine. I would have kind of done them separately, but they should be together because they always go together. They are related, sine and cosine. So let's remember that the Laplace transform of sine, of f of t will give the integral from 0 to infinity of f of t e to negative st dt. So that's the formula for Laplace transform. Now we're looking for the Laplace transform of sine. Let's see. So this will be the Laplace transform sine at, where the a is the constant. So a is going to be a number. So this will become integral from 0 to infinity of sine at e to negative st dt. And of course, at this part, we're going to be using integration by parts, but that's going to be a very tedious procedure. Yes, it's going to be a very, very tedious one, because then we have to then start integrating and probably looking for reduction formulas and all of the rest. So that's not necessary. Now, why is this not necessary? Because there's a way I can conveniently find the Laplace transform of sine and cosine. There is a way, because of course, if I can make this sine become some exponential, remember in the previous video, we've actually integrated e to the at. So is there a way I can make that sine become an exponential? Yes, of course. You need to remember that. You need to remember, I would have just written recall. You need to remember that e to the I theta is equal sine theta, cos theta plus I sine theta. You need to remember this. But of course, we do not have theta. What we have is at. So let's put that. This will be e to the iat equal cos at plus I sine at. Now, what does this tell me? This tells me that if I can find the Laplace transform of e to the iat, what I have to do is, to get the cosine transform or to get the Laplace transform of cos, I need to pick the real part of my answer. And then to find the sine, I need to pick the imaginary side of my answer. Now, of course, if you're in electronics engineering, you will notice that the I here is used as J. Most times it's just to avoid confusion for current. So we just prefer using J. So it's a thing of convenience. So you can decide to use I or use J, both of them meaning imaginary. So you can see that sine is the imaginary component, and then cosine is for the real component. So what I would do is, if I can find the Laplace transform of just e to the iat, when I'm done with my answer, I'm going to pick my real part, that's going to be cosine, and then my imaginary part will be my sine. So let's get started. So again, we know that the Laplace transform of f of t is equal integral from 0 to infinity f of t e to the negative st dt. So we're looking for the Laplace transform of e to the iat. So this will be integral from 0 to infinity. F of t is now e to the iat, and then e to minus st dt. So this is what we have. So what would I do next? Remember to use the full screen. The board is very large, so you see every single thing. Use the full screen and go to the settings and make the quality much more better, because the videos are going to be very clear. So what I would do is, let me do something of convenience here. Let me kind of swap these two. So this will be integral of 0 to infinity. You know, in algebra back then, algebra is all about manipulation. So we try to make things easier for ourselves. Now, in this case, I want to make something easy for myself by just flipping. So this one will come first. So this is e to negative st, and then e to the iat dt. If you noticed in the previous example, when I was flipping, I flipped it at the exponent. Like after I was done applying the laws of indices already, then I flipped it. But yeah, I'm flipping the two exponentials before applying the law of indices. So this will be integral from 0 to infinity. Now, they both have the same base. So this will be e. I need to add the exponents. So this is minus st plus iat dt. Beautiful expression. Now, you can see that t is common. T is common on both sides. So I can factorize t. So this will be integral from 0 to infinity. Then e. If I should factorize t, it's still not going to make my expression look so nice. Since this minus st is the first item, let me bring out minus t. You'll see why very soon. So let me bring out minus t. So when I bring out minus t, if I divide minus st by minus t, minus will take care of minus, t will take care of t. What's left is s. So instead of the minus being inside, let the minus be outside. And then plus minus is minus. Then t will cancel t. So what's left is ia. And then dt. So this is what we have. All right. Now I'm going to be integrating. So to integrate, what I will do is I'm going to write the whole exponential. So this is e minus t into s minus ia, then divided by the derivative of that exponent. So the power here, or the derivative of the power. So the power here, when I take the derivative with respect to t, this will become minus s minus ia. That's what I'm going to be getting. And then my limits from 0 to infinity. Okay. Now the next thing I'll do is, of course, for convenience, I like bringing out this denominator separately because this is with respect to t and our denominator does not have t. So let me bring it out. So this will be 1 over minus into s minus ia, and then we have e to minus ts minus ia from 0 to infinity. Now, let me save both of us. Let's save ourselves this stress. Let's actually save ourselves this stress. Remember that this bracket would always give you minus 1. I said it at the beginning. That will always give you minus 1. So there's no need for us to be imputing our limits. It should always give minus 1. So let's cut the crab. Abi? So this will become 1 over minus s minus ia times minus 1. Yep, in the previous example, I did something similar to this. I told you that just take note of it. With time, I will just put in minus 1. Because when you put in your infinity here, e to negative infinity is 0. And when you put in your 0 here, e to the 0 is 1. So that's a minus 1 because you are supposed to do upper limit minus lower limit. So that's a negative 1. Now minus will cancel out minus. So this will become 1 over s minus ia. Now, it seems as if we're done. Well, almost. We're almost done. So what I will do is this. Remember that back then when we're dealing with complex numbers, for a few of us, the first year in the university, you deal with complex numbers. So when dealing with complex numbers, we try our best to make sure our denominator does not have the item. And of course, even when you were doing SOD, the denominator cannot have its square root. So it's not just convenient for us. So all we're going to be doing is to rationalize. So to rationalize this, I'm going to say this is s minus ia. I will be timesing numerator and denominator by s plus ia. When I do this, I'm going to be rationalizing. So 1 times anything is that same thing. So this will be s plus ia. Now if you take a look at these two guys will make up a difference of squares. They are almost the same. The only difference is minus and plus. So what I will do is to say this is s squared minus ia squared. That's a difference of squares when you expand. So this will become s plus ia divided by s squared minus. Remember that you're going to be using the laws of indices here to say I squared a squared. So this will be s plus ia divided by s squared minus, what is I squared? I squared itself is minus 1. And then you put your a squared. So this will become s plus ia divided by s squared minus times minus is plus. And then you have a squared. Now we are almost done. Almost done. So this will be the Laplace transform of e to the, where is that? IAT. So it's giving us s plus ia divided by s squared plus a squared. Now let me split this expression into real and imaginary sides or imaginary parts. So for the real, I'm going to be having s. So this will be s over s squared plus a squared. And then plus the imaginary is the one having the I. So this will be ia, or let me just say, sorry. Let me say I, then a over s squared plus a squared. The denominator is a common denominator, so both of them must have the same denominator. And finally, what will be the Laplace transform of sine? Remember that sine is the imaginary side. Then what will be the Laplace transform of cosine? Cosine is the real portion of this exponent, is the real portion of the exponent. So finally, we're going to say the Laplace transform of sine AT. Sine is the imaginary. So when you compare them, this will become a over s squared plus a squared. Then the Laplace transform of cosine AT, that will become s over s squared plus a squared. Because while looking at this is for cosine, remember we have cos theta plus I sine theta. So by comparison, this will be for sine, and then this here will be for cosine. So that's just it. That's just it. All right. So we've now found the Laplace transform of sine and cosine. Now let's do something amazing. Let's take some examples so we use them as practice. So examples. We're going to say for the first one, let's take the Laplace transform of sine 4t. Now in this case, a is what? A is 4. Value of a is 4. So this will become 4 over s squared plus 4 squared. So that will be 4 over s squared plus 16. So with this, you have found the Laplace transform of sine 4t. Next, let's find the Laplace transform of sine 5t. Now what would this one become? We're going to be having, this is 5. So that would become 5 over, because a is now 5. A is 5. So this is 5 over s squared plus 5 squared. So that will be 5 over s squared plus 25. Very, very sweet. Next, example 3. Let's say we have the the Laplace transform of 2 sine 7t. First, remember that the 2 here is a constant. So I'm just going to be saying this will be 2 times whatever you have here. So what is the Laplace transform of sine 7t? This will become 7 over s squared plus 7 squared. So 2 times 7, that's 14 over s squared plus 49. And with this, we'll find the Laplace transform of these guys. Now let's take examples that involve cosine. Remember I said make sure your screen is set to HD so you can see all portions of the board clearly. So example 4, let's say we have the Laplace transform of cos 6t. Now in this case, a will become what? 6. So this will be s divided by s squared plus c squared. So this will be s divided by s squared plus 36. This is because when you compare these two things together, cos 6t, a is 6. So this will be s over s squared plus c squared, because a is equal to what? 6. How about another example? Let's say we have the Laplace transform of minus 4 cos 9t. Now for this one, remember that the minus 4 is a constant multiple. So this will be minus 4 times. Now for cosine, it's always going to start with s divided by s squared plus a squared. But a in this case is 9. So this will be 9 squared. It's going to become 9 squared. So this will become minus 4 times x is minus 4s divided by, this will be s squared plus 81. So this is what we have. These are examples for sine and cosine. Now, you need to share these very videos with your friends. Hit the subscribe button, like the video, because in the next one, we're going to be looking at hyperbolic functions. Please take note, we're not just doing this because for doing sake. We're doing this so that in the future, when we see problems, instead of going through all of these processes, we can just say, since we already know these two, so you have to practice with these two. Since we already know these two guys, we can find a Laplace transform whenever it involves sine or cosine. Now with this, let's take a look at hyperbolic functions in the next video. I'll see you there. Bye.